In this video, I will talk about the financial signal representation by wavelet transform. First, we talk about basis functions. In a 1D discrete wavelet transform, the basis functions are the sets of scaling functions and wavelet functions. So, as you can see, phi of x is a scaling function and psi of x is a wavelet function. J and K, K is used to shift the wavelet or a scaling function along the x-axis, and J is used to delete the wavelet or the scaling function. So first let's look at the Haar wavelet. Psi of x, which is the wavelet, is equal to 1 for x greater than or equal to 0 and less than 1/2, and it is negative 1 for x greater than or equal to 1/2 and less than 1. So if you plot psi of x, which is the wavelet function, then you get this. This is 0.5. And also there is phi of x. Phi of x is the scaling function and it is equal to 1 for x greater than or equal to 0 and less than 1 and 0 otherwise. So if you plot phi of x, then you get something like this. This is 0 and this is 1. And this is phi of x. And the other is psi of x. And there are other wavelet families as well, as you can see here. Okay, so now let's delete and shift the scaling function and see what we have. Okay, so if j is equal to 0 and k is also equal to 0, then phi 0 of x is actually equal to f of x. I'm sorry, equal to phi of x, and this is what you have. This is what you have. If k is equal to 1, then basically you shift the function phi of x to the right by 1. So if you go back to the previous slide and replace k by 1 and replace j by 0, and this is equal to 1 and that is equal to 1, and then you get this. Finally you get phi of x minus 1, and it is basically shifted to the right by 1. Now if you have j equal to 1 and k equal to 0 and replace similarly, right, they replaced j and k into the formula for 5 of x, then you get this. And similarly, 5 1 1 is actually still this, but shifted to the right. And this is actually equal to 5 of 2 times x minus 1/2, right? So from here, if we replace x by x minus 1/2, then we get this. And that also means we shift the function to the right by 1/2. So you see here, from here you shift the function by 1/2, then you get the other. Now if you have a function f of x, and the function can be, for example, expressed in terms of 510, 511, and 514. So if the function is like this, then it can be expressed using the basis functions 510, 511, and 514. And also a scaling function can be expressed in terms of other scaling functions. So this is the scaling function at the level j equal to 0 can be expressed in terms of other functions, other scaling function at level 1. Basically, when you go up in terms of level, the functions are shrinked or compressed, and you are able to use the function to express more detail. Okay, so in the illustration, we have several spaces. V0 is a subset of V1, and it's also is a subset of V2. And if a function f of x belongs to V1, V0, then we can express f of x in terms of the basis functions in that space. And basically, it is a linear combination of the basis functions in that space. And J0 here is the arbitrary starting level corresponding to V0. And also on this side, the space V0 is a union of V1 is a union of V0 and W0. This is V0, and that is W0, not including V0. And V1, this is V1. V1 is the union of V0 and W0. Then if a function f of x belongs to Wj, maybe W0, W1, etc., then the function can be expressed in terms of the wavelet functions in that space at level j. And here we can see the functions, the scaling function and the wavelet function are actually orthogonal, so they can be used as the basis functions. A function f of x is an element of v1, but not v0 can be expressed in the space v0 and then union with w0, and this is actually equal to v1. And here we have v0. v0 contains the approximation of the function f of x, and w0 contains the details of f of x. Okay, if we relabel alpha k, then the function f of x can be expressed as this formula. The first part is the approximation. Basically, you express f of x using the scaling function at level j0, and the rest, which is the detail, is expressed using the wavelet functions. And you start at level j0, and from j0 up to infinity. The higher j is, the more shrinked the wavelet functions are. And then at each level you shift using k, you shift the wavelet functions to the right using k. And here the coefficients c j0 is the approximation of the scaling coefficients, and dj is the detail or the wavelet coefficients, and the approximation of the scaling coefficients is the inner product of f of x and the scaling functions at the level j0, and easily you can get to this, which is the integral of f of x and the scaling functions dx. And similarly, dj is the inner product of f of x and psi jk, which is the wavelet functions, wavelet function at level j. And then you get to this. Now let's look at this example. If you have a function, a quadratic function x squared for x greater than or equal to 0 and less than 1, then c0 0 is equal to the integral from 0 to 1 of the function x squared, right? Phi 0 0, right? 0 0, and phi 0 0 is actually equal to 1 for x between 0 and 1. So simply taking the integral of x squared dx from 0 to 1, you get 1/3. And similarly, you get you compute, you calculate d naught 0, d 0 0. This is j and that is k. And um, in order to calculate this integral, you have to separate this into two integrals, because psi 0 0 is equal to 1 in the first half from 0 to 0.5, and negative 1 for x from 0.5 to 1. So basically you get two integrals, and this is the result. And simply following the same method, you get d1 0 and d1 1. And substitute all the coefficients in. We get this. And this is just the approximation, right? Approximation, and because this can continue and continue. And if you get just after this step, then you get the approximation, right? So up to here, this is actually V naught, right? And then that is W naught, and from here to here, this is V1. V1 is a union of V naught and W naught, and spanned by the scaling function phi 0 0 and the wavelet function psi 0 0, etc. And like the Fourier series expansion, the Wavelet series expansion map a function into a series of coefficients. And if the function expanded is a sequence of numbers, then the result are actually called the discrete wavelet transform. And this is a this is a discrete wavelet transform. It decomposes a function phi of x into the coefficients with the scaling, the starting scale j naught. So you get the approximation. This is the approximation and the detail. The approximation coefficient and the detail coefficients. And J naught is the starting level, the starting scale. Okay. And the inverse discrete wavelet transform is given as follow. Phi of x is equal to the first part plus the second part. The first part basically is the approximation of the function, and the second part is basically the detail of the function. Okay. In order to compute the discrete wavelet transform, we use an algorithm that called the fast wavelet transform. So basically, the detail coefficients at scale j are derived from the approximation coefficient at scale j plus 1. And similarly, the approximation coefficient at scale j are also derived from the approximation coefficient at the scale j plus 1. And the decomposition into the approximation and the detail coefficients can be repeated again and again, so that a multi-resolution structure is built. In the formula, h phi and h psi are referred as scaling and the wavelet function coefficients. So here we can see that the coefficient, the wavelet coefficients at scale j is derived from the coefficient, the approximation coefficient at scale j plus 1. And similarly, the coefficient at scale j, the approximation coefficient at the scale j is derived from the one at scale j plus 1. And this and that are actually the convolution. It's just convolution, and we can convert this form into this. And if we draw the decomposition step, and it looks like this. The approximation coefficients are decomposed into the wavelet coefficients at level j, and the approximation coefficient at level j, and from the level or the scale j plus 1.